Our last talk in the afternoon is by Régis De la Bretèche, and he'll speak on friable averages of oscillating multiplicative functions, arithmetic functions.
Thank you very much. So it's a pleasure to be here. So I would like to thank the organizer for giving me this opportunity to speak. So it was there, Andrew. So I remember that you came to visit me in Paris in 2008. So the main purpose was to improve your French. So it was maybe a success, and we get this opportunity to write an article together, and it was a pleasure. So then after you met my master student, Kevin Henriot, and then he decided to work to do a PhD under the supervision of you and me, and it was also a pleasure. So Kevin Henriot died 5 years ago, but his memory is still living. Okay. So I will speak about friable integer. So it was the subject of our first paper. I will write P plus n or P of n. It depends. It will denote the largest prime factor of integer n. So we will say that an integer will be a y variable if all its prime factor is less than y. So S of xy will be the set of y variable integer less than x, and psi of xy will be the cardinality of S of xy. So now I will take an arithmetical function f, and I want to study the sum of a y variable of f of n. So psi of xyf will be the sum of f of n on a y variable. And when y equal x, so that there is no hypothesis on the prime factor, I will not m of xf. So I need to say that what I will so this is a joint work with Gérald Tenenbaum, but I will present some result of literature to explain what we did. So the first part is not, well, it's an old story. So the story begins with De Bruyn, who find a clever approximation of psi xy. So if you want to use complex analysis to estimate such a cardinality, you will calculate the Dirichlet series zeta of sy. So this is a sum of a y variable integer of 1 over n plus power s. So we have an Eulerian product. You can write phi index y of s, the logarithm of this Dirichlet series. And maybe, as you know, if you want to estimate the integral here in the Perron formula, you need to choose carefully the the abscissa of integration, kappa, and you will choose kappa equal alpha, the saddle point, which is the solution of this equation. So minus the derivative of phi y of alpha equal log x. So when in a large domain, it's easy to find a good approximation of alpha, and this is a good way to approximate such integral, is to find carefully the abscissa of convergence. So this method was developed by Hildebrand and Tenenbaum nearly 40 years ago. And so this the integral can be approximated by this integral, so with a low ordinate, and then when you have alpha plus I tau, for example, tau not too big. Sorry, no, it's this. So here you know you have a bond on a tau. Then you can get a good approximation of the Dirichlet series. It's approximated by zeta of s time s index y. So s index y is s minus 1 time log y, time the Laplace transform of a function rho. So so it's a Laplace transform of rho in of sy, and rho satisfies the differential difference equation. So I wrote it here. So it's v, the derivative of rho in v, equal minus rho of v minus 1. So that's why I use difference term. And here, of course, well, it's not clear here, but rho of v is 1 when v is between 0 and 1. So now you see that in this part, we will see s minus 1 times zeta of s. We need to divide by s, which appears in the Perron formula. And then you will see that is a Laplace transform of a measure. So this part is the integral part of exponential v over exponential v. And so psi of xy is well approximated by this integral. So you see that this is a product of two Laplace transform times x power s. And if you take t, if you tend t to infinity, you will have a good approximation of a function which is lambda of xy, which is can be written as a convolution of two parts. So this is a convolution of the rho function and of the measure which appears here. So, well, one remark is that if x is less than y, this is a trivial approximation. Why? Because lambda of xy is just the integral part of x. So you approximate the integral part of x by the integral part of x. So it's not very clever, but after when x becomes larger than y, it gives good results. So this is so lambda of xy was first discovered by the brain, but the final result is due to Eric Sayas, which is a PhD student, which was a PhD student of Gérald Tenenbaum. So in the very large domain here, then you have a very good approximation of psi xy by lambda of xy. So you see 3 over 5 here, for example, is given by the largest zero-free region of the zeta Riemann function. So why is useful? So it's useful because lambda of xy is a kind of smooth approximation. So you can do a partial summation and you can apply it to estimate a lot of summation. And it's also useful because if you expand a row of u minus v with a Taylor development, then you can show a precise estimate of psi of xy. So you see this is x times a summation with a coefficient times the derivative of the row function in u. So u, of course, is log x over log y, over a power of log y with an error term. But this estimate is valid when you the fractional part of u, this is a fractional part of u, is not too close to 0 when u is less than capital J plus 1. And this restriction is very important. We will see in our result that it's very important to not to be too close to small u when u is, well, small integer. And this restriction is due to the fact that there is some discontinuity. Of course, a row of u, there is a problem of discontinuity when u equals 0. And then if you look at the derivative, there is a discontinuity in 1 and so on. But for capital J equals 0, it gives back the result of Hildebrand, so which the approximation of psi of xy in very large domain by x times rho of u. So if you don't know right variable theory, you can remember of my talk just by this very nice formula. So this means that you can estimate the density of y variable. So if y is x power 1 over u, the density is given by rho of u, and rho is satisfy differential difference equation. Okay, is it clear? So I will present more results. So now I will look at the same problem, but when you replace 1 by tau index kappa. So tau index kappa, of course, is defined by the fact that the Dirichlet series is the power of zeta of S. And kappa here is positive. It's a real positive real number. So if you remember what I did for when kappa equal 1, I look at the approximation of zeta of Sy So here now I will have zeta of sy power kappa, so that I will have in the approximation of the Dirichlet series the Laplace transform of rho power kappa, and this define function rho index kappa, and rho index kappa satisfies another differential difference equation, which is written here. So, this fact is very important. Why is very important? Because there is a very beautiful paper of Hildebrand and Tenenbaum in 1993, and this paper gives a complete study of such a function. The asymptotic, and this they succeeded to prove that f can be written in a basis of fundamental solution, and it's a very nice paper, and using saddle point method. Well, and so if you have such equation, you know that you can handle the asymptotic of the function by the paper of Hildebrand and Tenenbaum. I will approximate this term using the previous estimate. So I will write as this. So this is the power of two terms, and I will write s minus 1 at zeta of s power kappa over s times log y time Laplace transform of a function z index kappa in s index y. So z index kappa is also a solution of a differential difference equation. So the Laplace transform of this function is s power kappa minus 1 times the Laplace transform of rho index kappa. But you know, as rho of the Laplace transform of rho in S is asymptotic to 1 over S when the modulus of S tends to infinity, you see that this Laplace transform tends to 0 when S tends to infinity. So it's it defined a function. And then Andrew, Tenenbaum, and Wu prove in 2006 the same estimate as the Sayas estimate. So here there is an error term. I will not give much, I will not give more details, but you will see the main term is nearly the same as in De Bruijn approximation. So this is a function with a convolution with a measure of such a measure. So this is a summatory of the function of tau index kappa over y power v. And if kappa is an integer, then the domain may be enlarged. So this means that if kappa is an integer, the problem is much more easier. And as in Sayas result, we can expand this term. So we need to be not too close of an integer. So the fractional parts need to be large. So I give an explicit result here. And we have an expansion here as in Sayas article. Okay, so now I will speak of our new result. So now I will take a Dirichlet series of a function, and the function will be close to tau index minus kappa, with kappa is positive. So if you want an example, you take kappa equal 1, and you have the Mobius function. So that's why I write oscillating function, because you don't have a positive function, and then you want to estimate the oscillation, and also by getting an asymptotic of the sum psi of xyf. So here there is some assumptions. So I mean, if you want to simplify my statement, you take b equal 1, and you have you don't have any extra condition. The case when kappa equal 1 was treated by Aladi in 82, and after Tenenbaum in 89. So you use a complex analysis with Perron formula. And well, you see B of Sy here is the sum of B of S, but only on Y variable. But under suitable condition, you can approximate it by the Dirichlet series B of S. And then you can approximate the zeta of Sy by the previous estimate that I wrote here. And so you need to introduce the function h index kappa. This is z, but index minus kappa, so that h satisfy this differential difference equation. Between when v is between 0 and 1, h kappa of v equal 1. And we have this relation between the Laplace transform. So if you remember, the Laplace transform of rho is asymptotic of 1 over s. So this part is asymptotic to 1 over s. So it's a function, you can define it. Then you have the same kind of relation, so that this part s minus 1 times f of s over s is the Laplace transform of a measure. And then you can write this one as a Laplace transform of this main term, which is a convolution. So this is the same. And then you get the same estimate. So you see, well, if you want to know the extra difficulties, the main extra difficulties here is that the saddle point is not real. So there is two main saddle point, and you need to take as the abscissa of integration. This is the real part of the two saddle point. If you want to give an approximation as previously, it's become much more difficult. So we spent a lot of time to understand what happened. So for kappa is an integer. So this is my first assumption. You can expand h index kappa as previously, and you use this relation. This means that when j is small, so less than kappa, this is 0. And then we get the same estimate. Here the error term is with r index kappa function. I don't have time to speak about, but using Hildebrand and Tenenbaum result, you can give a precise estimate of this function. Okay, so now, yeah, I need also to say that when j equals 0, you have an estimate that it means that this functions tends to 1, but when j is non-zero, this term is 0, and you have an upper bound of the function which appears. Okay. So as previously, we have a good estimate in a domain where the fractional part is not too small when u is small. But now I need to have time, 2 or 3 minutes, to say that when kappa is not an integer, the situation becomes much more delicate. Why? Because the Taylor expansion of h index kappa is completely inefficient, because this integral, so this is a measure that we saw previously, do not converge for large j, and this asymptotic given, for example, by Selberg-Delange theorem cannot be exploited for small j. So then you need to write this Laplace transform as a product, but a product of a different form. So I write nu is the integral part of kappa, theta is the fractional part of kappa, which is now strictly positive, as kappa is not an integer. And we write this Laplace transform as a product. So we take a different product here. The good news is that phi kappa function satisfy a differential difference equation. But you see that here phi kappa is not equal 1 between 0 and 1. So there is a discontinuity in 0. But the general theory of Hildebrand Tenenbaum paper is still relevant. So I can express the estimate using the derivative of phi kappa. The new we derivate phi kappa new times, and then the main difficulties is now to give a good estimate of the function which is defined by this Laplace transform. So you can do it, and then we get finally the same kind of estimate, but also with a domain defined by the fact that the fractional part of U needs to be large when U is small. Okay, so I need to stop. But just to say that if the fractional part of U is small, then you have there is some extra term which can be bounded by such a term. So you see that if X is close to a power, integral power of Y, then this term is not small. Yeah, so now my final result is that the fact that if you look at the sum of a right variable of such a function f, then you can bound it by this term. So it means, for example, if f is tau minus kappa, this is a kind of trivial bond, and to compare to the trivial bond, we have this factor which tends to 0 when y tends to infinity, and you see the index of log y here is kappa plus m minus 1, and m is the minimum of the integral part of u and kappa plus 1. So it means, so if u is larger than kappa plus 2, then this part is kappa plus 1, and then the exponent is 2 kappa here. But if u is small, you get a smaller exponent in log y. So this result is the validity domain is x larger than y larger than 2. This means that we need to use another method when u is too large, and we use a result of Sari-Drapeau using a saddle point method. And this estimate is also was already proved by Tenenbaum when kappa is 1. Okay, so I will stop. So yeah, I just want to say happy birthday, Andrew. Yeah, so we are working on it with Gérald, and I think it will work. So so we have to check the details, but yeah, I hope it will work using this method. What will be? So you mean you get a smooth factor? Yeah. I don't know. Maybe you should ask her to sound, but I don't know. No, I don't know. Okay.